Hello everyone, this is Puya. In this video we'll learn more about cost functions and algorithm analysis and big O notations. Many of the examples in this lecture notes are from Dr. J. Edgar's notes, so I want to acknowledge Dr. Edgar's contribution. So to compare different algorithms for evaluation of their efficiency, we can implement them and just compare the execution time for both or like many algorithms that we have. However, this approach is not very satisfactory and very effective for different reasons. First of all, there's the effort that you have to put to do the programming and test two or many algorithms. When at best case you want to keep only one of them, the most efficient one. So like there's the effort to implement the algorithm. Secondly, like when you want to compare two algorithms, there's always the chance that one of the algorithms is implemented more efficiently, right? So like depending on which programmer implements the algorithm, so one of the algorithms might be better written than the other one. So like this is not going to be a very effective method to compare the algorithm itself, because the implementation, the programming language, the programmers skills, it's going to be also affecting the results. Also, the choice of test cases might unfairly favor one algorithm. So some algorithms might work much better for a specific test case than the other. So the choice of test cases is going to be very important when you want to implement the algorithms. And finally, the problem might be too difficult for implementation based on the resources that you have, like the software or hardware resources that you have, right? So the implementation might not be even possible to like compare many different algorithms. These problems can be often avoided by using asymptotic analysis. And asymptotic analysis measures the efficiency of an algorithm or its implementation as a program as the input size becomes larger. So we basically calculate the function, right? So we basically find the function of time depending on the size of the problem. So like time as a function, it's going to be dependent on the size of the problem. Like the size can be the size of an array, size of a vector, the number of nodes in a linked list. So this is an estimating technique and does not tell us anything about the relative advantages or disadvantages of these two programs or these two algorithms when one is always slightly faster than the other. Asymptotic analysis is proved to be very useful for computer scientists who must determine if an algorithm is worth considering for implementation for a specific problem. In this kind of analysis, we evaluate the performance of an algorithm in terms of its input size. So we don't actually measure the actual running time. We just calculate how the time or space or memory space that is taken by the algorithm is going to grow or increase with the input size. Like if the input size, like which is like the size of our array or vector or linked list or tree, so as this grows, we want to see how the time or space taken by the algorithm is going to increase. Asymptotic analysis also gives algorithm designers a tool for estimating whether a proposed solution is likely to meet the resource constraints for a problem before they want to implement it. So for example, before like we want to implement the program, we can just like see how much space we need, right? Like, it might not be even possible to implement it. or like how much time it's going to take for this algorithm to process a certain input, right? And it might just like be too like long or too much for us, so like it's not going to be a viable option. So before like even implementing the algorithm, you can decide whether this is going to be a suitable option for the specific problem that you want to solve. The critical resource for a program is most often its running time. However, you cannot pay attention to running time alone. You must also be concerned with other factors such as the space required or the energy that you have to put to implement the program. So these are other factors that you have to consider. So because of these reasons that we just mentioned, for general comparative purposes, we will count rather than time the number of operations that an algorithm performs. So instead of like measuring time, right? So we basically measure the number of operations or instructions that an algorithm performs. And we measure that as a function of our size, our problem size, or array size, or vector size. This does not mean that the actual running time should be ignored, right? So like it's actual running time, measurement of that, comparing that can also provide some insight. But this asymptotic analysis has been proven to be very effective when you want to compare different algorithms. Cost functions, or complexity functions, sometimes known as complexity functions, form the basis for algorithm analysis. Cost functions are what we use to compare algorithms at an abstract level, and they're functions that always grow, so they're non-decreasing, and it's typically using the size of the data collection and its domain, or its input, and we most often refer to as n, which is going to be the size of our problem, or the size of our data collection. And two things that we are most like focused on when we want to compare algorithms, it's the time efficiency and the space efficiency. So time efficiency is a measure of amount of time for an algorithm to execute, and space efficiency, or memory space efficiency, it's a measure of the amount of memory needed for an algorithm to execute. And we also like have this term like which we use in this presentation very often. So I want to introduce that function dominance provides a comparison of cost functions. So we basically, when we want to compare different algorithms, we find the cost function for both of them, and we'll see like which one is dominating to just figure out which one is going to be taking more time or taking more space. For simplicity, we assume that each operation takes 1 unit of time. It's not like a very exact assumption, but it's just like makes life easier for us. If algorithm on some input performs t operations, we'll say that it runs in time t, right? Because like we assume that each operation is just going to take 1 unit of time, whatever that means. Usually running time t depends on the data size, as we mentioned earlier, so the input length. We express the time t as a cost function of data size n. So we basically denote the cost function of an algorithm A as t of A function of n, where tan is the time required to process the data with algorithm A on an input of size n. Typical examples of the input size is the number of nodes in a linked list, number of disks in a Hanoi Tower problem, the size of an array, size of a vector, the number of items in a stack or queue or deck, the length of a string, and etc. An algorithm's efficiency can be described by either the time complexity or space complexity. So So both of them, complexity or cost, they're synonyms. Like complexity is more frequently used, like cost is less common. So like if you hear about cost function, is the same as complexity. Time complexity determines how long it takes for an algorithm to execute. In general, less time is better. And space complexity tells us like how much memory we need, how much memory the algorithm is going to use. And of course, less space is better. Costs are usually given as function of the size of the input to the algorithm. A bigger instance of the problem will take more resources, which is like more time and space to solve than a small one, right? So we know that if we want to process, let's say, an array of size 10, it's going to take us some amount of time. If we want to process an array of size 100, it's going to take us more time, and it's like it might need more space as well. We want to determine how much more space we need, right? So how the time and a space, it's going to grow, right? It's going to increase. The time requirement, space requirement, it's going to grow and increase as the size of our input is going to increase. For a given algorithm, if the size of the input is n, we would like to know T of n, which is the time cost of solving the problem, and S of n is the space cost of solving the problem. So here we want to see like an example of a cost function or complexity. So here like we have a function that goes through an array of size n and just prints all the elements of the array. Right? It starts from index 0, goes all the way to index n minus 1, and it prints all the elements of the array. Okay, so we assume that each operation takes a unit of time to execute. So how many operations do we have inside this function? So we have this declaration and initialization. We assume that it takes one, and here, right, we basically have n comparisons here, n increments here, and n n plus 1 comparisons, because here like we're gonna compare starting from I equal to 0. Even when I becomes n, we're gonna compare. So we have n plus 1 comparisons here, n increments, and n cout, right? So so we see that like we have 3n plus 2, that's our cost function. This is like the cost function for this C++ function that we have here. This is the complexity, the time complexity of this problem, right? So it shows basically how t is going to increase as n increases, right? So this is an example of cost function. Another example here, let's say that we want to find the average value of all the elements in an integer array. Again, like you see that here we have initialization and declarations, like 2 here. We have a loop, have n plus 1 comparisons here. We have n increments here, another n increments here, and like a if statement here, right? So like this is and one else statement, right? So like either of these is going to be executed, so like 1 or 1, right? And the total cost is going to be 3n plus 5. Okay, so this is an example of cost function again. This is another example where we have nested loops, right? So here I changes from 1 to n, j changes from 1 to I, and k changes from 1 to 5. Okay, so this one, it's easy to calculate how many operations we have. Like task t, like it just like has like 5 iterations throughout this loop if we ignore the outer loops, right? But for these two, right, we know that we go inside this loop n times, right? But for this one, it's not as easy to calculate, right? So like we have to basically the number of iterations that this loop has depends on the value of I. So for each I, we have to calculate how many times we go inside this second loop, right? If I is equal to 1, we're going to go inside this loop once. If I is equal to 2, we're going to go here twice, and so on, right? So the number of times that we go inside the second loop, it's this summation. The number of times, like for each time we go here inside the second loop, we're going to go inside the third loop, the most inner loop, 5 times. So it's going to be multiplied by 5. So the time complexity of this problem, it's going to be, and here t is like the unit of time, right? So the time complexity of this, if you assume that t is 1, it's going to be 5 times n multiplied by n plus 1 over 2. This like summation can be calculated as n times n plus 1 over 2. So this is the cost function for this problem. Since cost functions are complex and maybe difficult to compute, we approximate them using big O notation. Big O notation determines the growth rate of an algorithm time and approximates the cost function of an algorithm. The approximation is usually good enough, especially when considering the efficiency of algorithm and as n gets very large. So this is a very important point here. So big O notation is usually a good approximation when we are talking about very large sets of data, right? If n is about like 10 or like 100, like this is not going to be a very good measure probably, right? But as n gets very large, this is going to give us like a better insight about the efficiency, the time efficiency or space efficiency of an algorithm. Instead of computing the entire cost function, we only need to count the number of times that an algorithm executes its most critical operation or most critical instruction, also known as barometer instruction, right? So the instruction that gets executed the most. The instruction is that executed the greatest number of times in an algorithm, the highest order term. Okay, so again, like you see here, like another example of a cost function. So you see that if this is like cost function, this is going to depend on n, right? And you have to know like which term dominates. If you want to estimate the behavior of this function, we basically want to know which term dominates. This depends on how big or how small n is, but as n gets larger, we know that n squared, it's going to be the most dominant term. But if n is a small, right, then like 100 might be even the most dominant term. So the idea for that is that the cost function can be approximated by another simpler function. This simpler function has only one variable, which is the data size n, and this function is selected such that it represents an upper bound on the value of tan. Okay, so we want to have like an upper bound for this cost function or this complexity function that we have. So as mentioned, like it can be difficult to determine the exact number of operations performed by an algorithm. It is possible and it's like useful to do so, but it's like very difficult in some cases. So an alternative solution is to count all instructions. Instead of like counting all the instructions, we want to focus on the most critical instruction or barometer instruction. This instruction is the operation that is executed the most number of times in an algorithm, and the number of times that the barometer instruction is executed is usually proportional to its running time, right? So like this is like how the time complexity can be measured by the number of times that this most critical instruction is executed. So for example, if we want to look at this example, which is the linear search, the most critical operation, right? First of all, this depends on our array and our target value. So we're gonna have a worst case, a best case, an average case, right? But if if you want to know like which one is the most critical operation, right? In the worst case scenario, this one, like we know that it only gets executed once, right? But this one can be considered the most critical operation, right? Because like it gets executed, like if the target doesn't exist in the array, it's going to be executed n plus 1 times, right? And we can have multiple of these barometer instructions. So like here, this is going to execute n plus 1 times in the worst case, this one n times, and this function, this if statement n times in the worst case scenario. But this one, it's going to only get executed either 0 times or once. The same thing for here. Okay, so this is like how we should determine like which one, which statement or which instruction is the most critical one. So this is just like a review of the concept of asymptotic dominance or asymptotic analysis. Asymptotic dominance is used for comparisons of cost functions when n is large. We see, like usually like around thousands or millions of data points, not just like 5 or 20. Formally, the function g of n is said to be symptotically dominating the function f of n if there are two positive constants c and n sub 0, such that c times gn is bigger than equal f of n for all n's bigger than n0. This is like the mathematical definition of asymptotic dominance. Basically means that just like this function is going to be the upper bound of f of n, right? For any n's bigger than a certain n sub 0, right? So like this is just like the definition of asymptotic dominance. So we mean like function gn asymptotically dominates function f of n if c times gn dominates f of n for all large values of n larger than some threshold value n sub 0. Or another like way of saying that is like c times g of n is always bigger than f of n for values larger than n sub 0. At some point, g of n is always larger than f of n. We're always interested if n sub 0 exists. We want to know like if there is a number that like for all n's bigger than that number, g of n is going to dominate f of n. Otherwise, g wouldn't dominate f. Sometimes we are also interested in the actual value of n0, so we want to figure out at one point g of n is going to get definitely bigger than f of n for all n's. So the value of c is rather not important, and we are interested if we can, we are just like interested if we can find one, right? So in our study of algorithms, nearly every function whose order we are interested in finding is a function that defines as the quantity of some resource consumed by an algorithm in relationship to the parameter of the algorithm. This is like a very difficult sentence to understand, but basically means that like time or space, like these are going to be functions of like some resource, right? So right, the function is this function is often referred to as complexity of the algorithm, or less frequently as the cost function, right? So this is like the formal definition of cost function or complexity. This function is a property of the algorithm. For example, when we are analyzing an algorithm that multiplies two numbers, the functions we might be interested in are relationships between the number of digits in each number and the length of time or amount of memory required by the algorithm. So previously I mentioned that like we always like find the cost function as the input, like as a function of n, the number of items in our array or in our vector or in our linked list, stack, queue, deck. But in more general term, like when we talk about complexity and cost function, in like the input or like our function might be depending on other things, right? So like this is like the more general definition for cost function. Note that this notation, like the order themselves, doesn't tell us how quickly or how slowly the algorithm executes, right? So like based on the cost function itself, you don't know, like you don't have any measure of time. Several algorithms that address the same problem and have the same order running time, they might take substantially different amount of time to execute. We've seen that before. We've seen like many different algorithms with the same cost function or big O notation, but they're going to be running and executing instructions in different amounts of times. Similarly, the order doesn't tell us how fast an algorithm will run for a small n. So this is also like an important point to remember. I've mentioned this a couple times so far. So for many group of algorithms, the choice of the best algorithm depends on n, right? So when n is a small, one algorithm might be better, but when n is large, a different algorithm is much better. We've seen that in sorting. We talked about like different cases for sorting, like if n is huge or like very large or very small, which sorting algorithm might be a better option. This is what we were talking about, like about asymptotic dominance, and like this is the formal mathematical definition of big O notation. So if we find the complexity or cost function of a problem of an algorithm, let's say if it's f of n, if we can find an n sub 0 for which there is a function g of n where like c times g of n, it's going to be always greater than f of n for any n bigger than n0, right? We say that g of n is dominating f of n, and we also say that f of n is of big O notation g, right? So this is basically the formal definition of big O notation. We usually want to find the tightest function, the or like smallest function that would be dominating f of n, right? So like let's say like if the f of n or t of n, like here t is short for time, so if t of n is 3n plus 5, all of these functions, n squared, n log n, 2 to power n, like all of these can be like g of n. All of them can be g of n, and all of them are going to be dominating f of n at some point with the proper choice of c and n0, right? But we want to find the tightest one. So like here we always say that our big O notation of this function is order of n. Okay, so we don't want to go with the higher order terms. So this basically shows like how we can find like these n sub 0 or this constant here. So like for different examples, let's say that we find the cost function of like an algorithm and it's 3n plus 12, right? And we know that this is going to be of big O notation n, right? But like we want to know that what is going to be this number n0. So at what point this function is going to dominate it, and like what's the choice for c, right? Here like it's using different symbols, right? So like this is like the dominating function. So we know that k times n, it's going to be bigger than equal to 3n plus 12 for all n's bigger than a certain threshold value, right? So we want to find some values for this k and this m, right? So we know that, right, if this is 3n plus 12, we know that 4n, it's gonna be, so like if we write this one as 4n is going to be 3n plus n, right? So 3n's are going to cancel. We know that for all n's bigger than or equal 12, 4n is going to be greater than or equal 3n plus 12, right? So like here we can find k to be 4, and this threshold value, which here like we showed as n sub 0, here it's shown as m, it can be 12. Another example here shows another cost function, 2n squared plus 10m plus 6, right? Again, like you know that this is going to be the dominant term. We know that the big O notation for this one is big O of n squared. But we want to find out, okay, for what value of coefficient k times n squared, it's always going to be bigger than 2n squared plus 10n plus 6. And like what is going to be the threshold value? So again, so if we write this one here, 2n squared plus 10n plus 6, if we choose k as 3, right? If we choose k as 3n squared, right? So it's just basically so like we can write 3n squared as 2n squared plus n squared. 2n squareds are going to cancel, right? So it's going to be n squared is going to be bigger than or equal 10n plus 6, right? And for that one, if we choose m to be 11, we know that this is always going to be the case. 3n squared is always going to be bigger than 2n squared plus 10n plus 6. Think about this, and like maybe you can come up with like other values for k or m, right, for the same big O notation, right? Like you can find other values for k and m and see like why this is the case, why 3n squared is always going to be bigger than 2n squared plus 10n plus 6, right? So like here, like we know that like n, so we basically have to prove that n squared is always going to be bigger than 10n plus 6. How can you prove that? Like, and like what is the threshold value? We know that for the growth of a function, the highest order term matters the most. So like here, if we have a cost function like this, c sub 1 n squared plus c sub 2 n plus c sub 3, the first term, c sub 1 n squared, is the dominant term. And we're going to use this one for the big O notation. Right, so even with these approximations, we'll be able to know about the rate of the growth of our function, and this is enough information to keep in our mind while developing an algorithm. So we are doing like a lot of approximations. We are ignoring like multiple terms, right? But even with those approximations, like big O notation or asymptotic dominance provides a relatively good mechanism to compare different algorithms. Different cost functions or complexities that we have seen in this course or your previous courses, like that's been the constant function, linear function, quadratic function, cubic function, can be logarithmic function, what we call like superlinear function or like n log n time complexity, exponential functions, and factorial functions, right? And these two plots basically shows like how these functions grow as n increases. And you see like why like this n factorial is shown last, right? This is gonna grow very, very fast, even faster than 2 raised to power n. Okay, so this also shows you the comparisons for the big O notation of different algorithms, right? Which one is going to be more dominating. Some simplifying rules, like we don't use them very often, but if f is like f is always order of f, right? A function can be its own order, right? This like here, like our function is basically our cost function. These are like mainly used in like pure mathematical part of computer science, but like it's good to know. Big O notation of k times f, it's gonna be big O notation of f, so we don't care about the constants or coefficients. Big O notation of f plus g, it's going to be of order of maximum of order of f and order of g, right? So here, like you can assume that here, like if this is f, this is g, right? This is going to be of order n squared, and this is going to be of order g. So we always like care about the most dominant term. If you multiply them, it's just going to be, the orders are going to be multiplied. If you're going to divide them, it's going to be divided. Order of f is going to be bigger than order of g only if f dominates g, right? If you have subtraction in your cost function, don't assume that f of n minus g of n, if both of them have the same big O notation, it's going to be equal to 0. So for example, you see that here f of n is 2n squared, g of n is n squared. Subtract them, it's going to be n squared. It's not going to be 0, right? So this is going to be of big O notation of n squared as well. The powers of n are ordered according to the exponent, right? So n of a, it's going to be of order n raised to power b if and only if b is greater than or equal a, right? But we always want to find the tightest function, right? So like we're just going to be, in this case, it's going to be order of n of a. The order of log n is independent of the base taken, right? So that's why, like in big O notations, in many cases we don't show the base. However, like if we actually want to compare the time consumption, time execution, like execution time, we often are interested to looking at different logs. Higher log basically is actually better, right? In terms of big O notation, they're going to be the same, but higher log, it's basically better. Most often in most algorithms that we have seen so far, the log was in base 2. Log functions grow more slowly than any power of n, right? So log of n is basically like growing much slower than any order of n, like if a is bigger than 0, right? So like here, but you can't say that n raised to power a is order of log n, right? It's just like this is going to be growing much faster, right? So it's like this one is true, but that one is not true. The same thing that we mentioned about the power functions here, like we have it here. And so like here, like we basically, something that we have to know is that if we want to compare n squared and 2 raised to power n, right? 2 raised to power n is like it's growing faster, like for large values of n, 2 raised to power n grows much faster than n squared, right? And this is true for any other number as well. Something that we've seen in our course in many different examples is that like we always want to get like order of 1, right? So we always like are interested like in doing algorithms like much faster, right? Like if possible, if not log, if not linear, if not basically super linear, or like so on, right? So we always like consider this as a good thing, like as a very desirable thing. However, like you have to know that like any constant any cost function that has just like a constant, it's going to be of big O notation 1, right? So big O notation 1 means that like our function's execution time or auxiliary space that occupies does not depend on the size of the problem. It's always going to be a constant, but it it doesn't say anything about the value of that constant. That constant can be 1 or 2 or 10, or it can be billions, right? So if a cost function is like 2 raised to power 10,000, it's still considered big O notation of 1, right? Because this doesn't depend on n. There is no n in it, right? So just like have to consider that, like it's not always like a desirable thing. Like you have to like be careful about that as well. When we want to compare algorithms, as mentioned earlier, right, in many cases, like it's just not simple. We have like ifs, we have like breaks, we have like many different like returns like in our functions that we just basically doesn't have like it, like we don't have like a linear execution process, right? So like there might be jumps to different parts of the program. So we usually want to study three different cases: best case, worst case, and average case. Best case is very optimistic. Worst case is pessimistic but useful for an upper bound on the cost, and best case is useful for finding a lower bound on the cost. Average case is very useful, but it's more like challenging to find. Like there's always lots of like difficult math involved to find average cases. If you remember when we were talking about hashing, we talked about average cases, and there's a lot of nasty math behind all those calculations. There's like usually probability involved, like discrete math involved. So it's very useful, but it's like hard to analyze. So I'm not going to spend much time on these examples. We have done it in the previous video. This is a selection sort, right? So like you know that we have nested loops here. The number of times that we go inside the outer loop is fixed, but the number of times that we go inside the inner loop depends on I, right? So we have to analyze it for each case, for each I, right? So, and then all other thing that we have to find out is the most critical operations and the cost function. So this here, like it shows like how you can find the total cost. We did some sort of analysis like this in the previous videos, right? So like this basically shows the total cost for this function. And if we just like find the most dominant term and ignore like all the coefficients, it just like basically shows that we would have a big O notation of n squared, right? So here again, the most critical or the barometer operation instruction is this if, right? Is this if that's like it's going to be executed the most in the worst case scenario, right? So like here, if you want to consider the worst case scenario, right? So like this is what we have to do. Okay, this is the function. This is like the operation that we can count how many times it gets executed. This also shows you like the same problem that we had before. Like if we want to find the big O notation for this one, we want to find the worst case scenario in this case, right? So the worst case scenario for linear search is going to happen when the element doesn't exist in our array, right? The target doesn't exist here. So if that's the case, it basically this operation, it's going to get executed n times, right? So then and the like, so just like you can either find the big O notation of the problem based on only the amount of time that this operation gets executed, or you can actually find the total cost function, right? Both of them should give you the same big O notation. Here, so like I mentioned, the average case analysis is is more challenging than finding the best case scenario or the worst case scenario. If we want to analyze the same linear search and we want to find the average case analysis, let's go through the slides that Dr. Edgar prepared for us. So here, like if there are two situations when the worst case arises, right? When the target is in the last item in the array, or when the target is not in the array. If we want to find the average case, we need to know how often these two situations arise. So here we have an assumption, right? We have an assumption. This is not going to be a very exact assumption. So like it's just like this assumption may not hold for a specific particular instance of linear search, but like here we assume that the target is not in the array half of the time and half of the time is in the array. Okay, so half of the time the entire array has to be searched and half of the time we find the target. Assume that there is an equal probability of the target being at any location. So we have n locations in the array and the probability of just like the target being in any of these location is basically going to be 1 over n, right? So because we have n elements, right? So the probability of being at location 0, 1, 2, 3, it's going to be all the same, right? So then so it means that the probability of the target being at a specific location I, it's going to be 1 over n. Okay, so if the target is not in the array, we have to do n comparisons. And this happens like based on the assumption that we have, it's going to happen with the probability of 0.5. If the target is in the array, right, we might need to do one comparison if the target is at the first location, right? What's the probability of this? It's going to be 1 over n. We might need to do two comparison if the target is at the second location. What's the probability of that? It's going to be 1 over n. And the same thing, it's going to be applied for any other location, any other element. So if we find the weighted average of all these values, right? So like we basically multiply the number of operations by the probability of that case happening, right? If we do that, we end up with this expression. If target is not in the array, we have to do n comparison. If target is in the array, on the average, we have to do n plus 1 over 2 comparisons. And we know that this, like based on this assumption that we have, this happens half of the time and this happens half of the time. So again, like we do another weighted average and we find this one. So this is basically the average case analysis for linear search. So this is like how the average case analysis is done. It's like usually lots of probability is involved, lots of discrete math, lots of series calculation is involved. Okay, and recall that like this like all of this is based on this assumption. This assumption might not be true for a specific example. The other two notations that I want you to just know them and hear them, like we don't use them in our course, but it's very good to know, especially if you choose to do computer science. The big O notation was used as the upper bound for our cost function. There is another one, big omega notation, which is used, big omega is used for the lower bound of our cost function, right? So like the same thing that we had for big O, like we have it for big omega, but this time it's going to be the lower bound. Okay, and again, we want to find the tightest g of n, right? So the one that's closest to f of n, right? So there's going to be many different functions that can provide a lower bound for f of n, but we want to find the one that's closest to f of n. And big theta notation basically provides both upper and lower bound for a cost function. So if g of n is both is a function that can provide both upper bound and lower bound for f of n, right? So f of n is going to be of theta g of n, right? So this is basically providing both upper and lower bound. So here, like f of n is basically getting sandwiched between two instances of g of n. Okay, so that's the big theta notation. Thank you so much. Have a good one.